Lesson 5 is our third of 3 introductory lessons on algebra, and again, this should mostly be a review for you. And just think about a basketball player. A basketball player, before they start a game, they'll do like fundamental things like layups, things that they've been doing for a very long time. It's no different here. I don't expect you to have everything memorized. Hopefully most of this will be easy for you in these first 25 lessons with some new things here and there. But you should be really familiar with things like Part A, quadratic equations. And our focus in Lesson 5 is mostly on nonlinear equations, where Lesson 4 was more on linear equations. And as with Lesson 4, though, there's a deep connection to this lesson and analytical geometry. You'll review graphing nonlinear equations in Lessons 9 through 13. So to begin here, let's review finding roots or zeros of basic polynomial equations. And start with example 5.1. Find the roots of the following polynomial equations. Not all of them are quadratic, but we can break them into quadratic components. So begin each one by setting y equal to 0. So the second degree polynomials, those factor into two binomials like a typical quadratic relationship does. The third degree, they're designed to factor into a quadratic polynomial, which in turn will factor into two binomials. So A, x squared plus 2x minus 3. Let's factor that. That would just be two binomials. Two numbers multiplied together equal negative 3, added together equal 2. That'd be a plus 3 and a minus 1. So we'd have x plus 3 times x minus 1 equals 0. That's what it means to find the roots or find the zeros of a polynomial equation. When would it equal 0? Well, inside those parentheses, if either of those equals 0, then the whole thing equals 0, right? Because x plus 3 is a factor, x minus 1 is another factor. So the opposite of 3 is negative 3. If we had minus 3 plus 3 right here, then that factor would be 0, right? And the whole thing would be 0. So that's all you have to do on these, is find the opposites of those constant terms. X plus 3 minus 3 is the opposite. X minus 1 plus 1 is the opposite. So x equals minus 3 and 1. Those are the solutions. Those are the roots, also known as zeros. B, y equals 3x squared minus 15x minus 42. So factor that into 3x and x. And then think two numbers multiplied together equal negative 42. That'd be like a 7 and a negative 6, or a negative 7 and a positive 6. But how would we get 15x in the middle? Well, 3x plus 6, x minus 7, that would work. Set it equal to 0. What x values would make that left side equal to 0? Well, with 3x plus 6, we need a minus 6 plus 6. So 3 times negative 2. X equals negative 2. That works. And then plus 7. Because 7 minus 7, that would be 0 in there. So x equals minus 2. Not plus 2, but minus 2 and 7. Those are the roots, or zeros. On C, we have a third degree polynomial there, x cubed plus 2x squared minus 15x. But notice we can factor an x out. So let's do that over here on the left. Let's do that first. X parentheses x squared plus 2x minus 15 is equal to 0. And then let's factor that. That's said in the instructions. This would factor into two binomials. So x parentheses x plus 5 times x minus 3, that works, equals 0. So we have three possibilities for factors here that would make that left side equal to 0. One of them is just 0 because of this x right here. If that's 0, then makes everything else 0. And then for the binomials, it's just the opposite. So a minus 5 plus 5, that'd give us a 0. A plus 3 minus 3, that'd give us a 0. So x equals minus 5, 0, and positive 3. Those are the roots or zeros. And just thinking about our rules, the fundamental theorem of algebra, any polynomial of degree n has n complex roots. So those are all complex numbers, -5, 0, and 3. Complex numbers have that form a plus bi, the real part plus the imaginary part. It's just that the imaginary part is 0. That's what real numbers are. They're complex numbers with an imaginary part of 0. Remember, you're supposed to read over the rules and definitions before you start a lesson, so what I just talked about should already be familiar to you because it's described in the rules. Now, not all quadratic relationships factor easily into two integer value binomials, which makes it real easy to find the roots or zeros. So if you want to find the roots or zeros of any quadratic relationship, then you can use the quadratic formula. And in the reading assignment, and also in Shormann Algebra 2, we derive that quadratic formula from the standard form of a quadratic equation, ax squared plus bx plus c equals 0. So I won't repeat all of that here, but you can look at the reading assignment. It's explained there how to derive the quadratic formula. You use the completing the square method to do that. So anyways, we'll just dive right into it here and apply the quadratic formula to a. And a good first step on these is just to think about your standard form, ax squared plus bx plus c equals 0, and what is a? Coefficient a for problem a. It's 2. B is 5. C is 1. And so for the quadratic formula, we have x equals negative b, or negative 5, plus or minus the square root of b squared, so that'd be 5 squared, minus 4 times a is 2 times c is 1, all over 2 times a, or 2 times 2 is 4. So that's equal to minus 5 plus or minus the square root of 25 minus 8, that's 17. All over 4. And so normally we break this up into two parts. X equals minus 5/4, and then the plus or minus part. Plus or minus the square root of 17 over 4. Because sometimes that plus or minus part is an imaginary number, so we can have it in its real and imaginary components. X equals negative 5/4 plus or minus the square root of 17 over 4. So just like in example 5.1, you get two solutions for a second degree polynomial. That's what you'd expect based on the fundamental theorem of algebra. And just a reminder here, if you are like totally clueless about the quadratic formula, x equals negative b plus or minus square root of b squared minus 4ac all over 2a, then that's a big red flag for you that you should actually be in Algebra 2, not Precalculus. So you should by this time be so fluent with the quadratic formula that you know exactly what I'm talking about the a, the b, the c, and where to put them, and what the quadratic formula is. Well, let's move on to b. And this time, a is 3, b is negative 2, and c is 1. So we start with that, substitute into the quadratic formula. X equals negative times negative 2 is plus 2, plus or minus the square root of negative 2 squared, so it's negative 2 times negative 2 is 4, minus 4 times a is 3 times c is 1, all of that over 2 times 3, 2 times a, is 6. So that's going to equal 2 plus or minus the square root of 4 minus 12. That's a negative 8. We have a square root of a negative number. That's going to be an imaginary number. But let's just keep simplifying. 2 plus or minus square root negative 8 over 6. So then we'd have 2 plus or minus 4 times negative 2. We try to factor out something we know the square root of 4. So we can say plus or minus square root 4 times square root negative 2 all over 6. That equals 2 plus or minus 2 square root 2i. Square root of negative 2 is the square root of 2 times the square root of negative 1, right? And square root of negative 1 equals I. So that's, instead of having to write square root of negative 1, we write I instead, right? That's what we talked about in lesson 1. All over 6. Do you see how that's going to reduce now? We can factor a 2 out of all of that and cancel. So x is equal to 1 plus or minus the square root of 2i all over 3, which equals 1/3 plus or minus the square root of 2i over 3. So that's how we want to write that, as that real part 1/3 and then the imaginary part square root 2i over 3. Let's do one more. Y equals x squared plus 4. Now you could recognize on that one that you could just say x squared plus 4 equals 0. There's no x term in it. So you don't need to use the quadratic formula. In the reading assignment example, I use the quadratic formula. So you can see how to do that there. But really, all you have to do on this is just say, well, x squared is equal to negative 4. Take the square root of both sides. X is equal to plus or minus the square root of negative 4, which would be square root 4i, which is equal to plus or minus 2i. Those are your two roots, two complex roots, which really these are two imaginary roots because there's no real component to them, unless you wanted to write 0 plus or minus 2i, where 0 is a real number. But we'll just leave it like that, plus or minus 2i. Let's move on to part B in absolute value equations. And as with quadratic equations, you normally get two solutions when you solve them. However, we're not finding zeros here because we're not starting by setting y equals 0 as you did in example 5.1 and 5.2. What we're doing is we're finding the values that satisfy the following equations. So for example, in A, we're finding the value or values that make that left side equal 9. Not 0, but what makes that 9. And that would equal 9 when x plus 2 is equal to 9, or when x plus 2 is equal to minus 9. Because the absolute value of 9 or minus 9, that equals 9, right? So look, we solve both of those equations now. So on the left, we'd subtract 2 from both sides and get x equals 7. On the right, we'd subtract and get x equals minus 11. Both of those values, 7 comma minus 11, those are the two solutions there. That would make the left side equal 9. A minus 11 plus 2 is minus 9. Absolute value, that is 9. 7 plus 2, absolute value, that is 9. Same thing with B. You might want to pause the lecture, see if you can figure that one out on your own. And a first step on that would be to get the absolute value term isolated, then make your two equations. So here we could start out with absolute value x minus 5 is equal to 6 minus 4 is 2. Now we want to know absolute value x minus 5 when that equals 2, or when that equals negative 2. Because that's what's inside the absolute value bars, right, is the x minus 5. So that can equal negative 2, or it can equal positive 2, because when you take the absolute value of it, it just gives you 2. So solving those two equations, we get x equals 2 plus 5 is 7. X equals minus 2 plus 5 is 3. So x equals 3 and 7. Those are the two solutions. Part C is on radical equations. So a key attribute of those is that in order to give a real number solution, the isolated radical must be greater than equal to 0, because you can't take the square root of a negative number. So that's an easy way to know if we're actually going to get a solution or not on these. And sometimes you can just stop the problem if you recognize that. So A, start with that one, solve that, isolate the radical first. So we have square root x plus 4 is equal to 6 plus 2 is 8. Now, get rid of the radical sign by squaring both sides. Then we just end up with x plus 4 on the left is equal to 64 on the right. Subtract 4 from both sides, x equals 60. That's our solution. Does that work? Does that work back in the original equation? If I substitute it in there, square root of 60 plus 4, that'd be a square root of 64 minus 2. That equals 8 minus 2 is 6. Yes, that does work. So we did that correctly. B, it's always what you can do on these two is check your work that way to make sure everything worked out. Isolate the radical first. Square root x minus 2 is equal to 3 plus a negative 9. That's a negative 6. Square root of what equals negative 6? Well, square root of nothing equals negative 6. You can't do this problem. You can try. In the reading assignment, you can see how we tried to solve it, but then you substitute it back in, it doesn't work. So you can just stop right there and say empty set. C, let's erase this so we have room for C. And notice the x on the right side, that doesn't matter as far as isolating the radical. We isolate the radical first on these. So let's do that. Square root x squared plus 2x minus 5 is equal to x minus 2. Now, we've isolated the radical. We can't really tell anything as far as is this going to work or not. So we just need to go ahead and square both sides to get rid of that square root sign. So then we'd have x squared plus 2x minus 5 is equal to x minus 2 times x minus 2. That's x squared minus 4x plus 4. Simplify that down. Notice the x squareds would cancel, and we get 6x is equal to 4 plus 5, 9. X equals 9 over 6, which would be 3/2. Now, we need to check that. Is that going to work? Make a little box here. The square root of, got a big term here to work with here. X squared, that'd be 3/2 squared, that'd be a 9 over 4. Plus 2 times 3/2, that'd be a 3, which in terms of fourths, 3 would be 12 over 4. Minus 5, that would be, in terms of 4, that'd be a minus 20 over 4. And then all of that plus 2. Does that equal 3 over 2? Well, let's keep going here. What do we have here? We have the square root of 9 plus 12 is 21 minus 20. That'd be a 1 over 4. Square root of 1 over 4 is 1/2. So what we have there is 1/2 plus 2 is equal to 3/2. That doesn't work. So the answer is like B. The answer is empty set. There's no solution for that equation. But we didn't know until we checked our work on it. You couldn't tell on that one. On B, you could tell right away because you had the radical on the left and a negative number on the right. You can't take the square root of a negative number. The square root of something doesn't equal a negative number. On C, we had to check our work. So that's something you might want to make a note of is problems like problem C, you have to check your work on them. You have to solve them first. Part D is on exponential equations, and solving these is not too different from simplifying problems like example 2.4, where it helps to be observant, recognize a number or numbers that can easily be rewritten with a particular base and exponent. So in other words, these are designed to simplify into fairly simple integer values. So for A, to get rid of the 3/2 exponent, we could multiply both sides by the power of 2/3, right? We could raise both sides to the 2/3 power. So let's do that. X to the 3/2 to the 2/3 power. And we have to do the same thing to the other side. We can't just leave the other side as 8. We have to say 8 to the 2/3 power. So that means we have on the left x to the 1, right? Because 3/2 times 2/3 equals 1. So now we have x. But on the right, what is 8? 8 is 2/3, right? We have 2/3. Put it in parentheses. 2 to the 3rd, not 2/3, 2 to the 3rd, raised to the 2/3 power. So now we have 3 as an exponent, which is 3 over 1, right? 3 over 1 times 2 over 3. The 3's would cancel. We're left with 2 squared. That equals 4. And that's it. A simple integer answer. On B, notice the base of 2 on the left. So think, can I make the right side have a base of 2? Well, yeah, 16 is 2 to the 4th. 2 to the 5x equals 2 to the 4th. If we have similar bases there, the exponents should equal each other. So 5x equals 4. X equals 4 over 5. C, look at the bases, 3 and 9. Well, 9 is 3 squared, right? So we could get the bases to be the same and then set the exponents equal, kind of like what we did in B. 3 to the x plus 1 is equal to 3 squared. So I have to say 2 times the 2x minus 3 that's already there. And so now we're just saying x plus 1 is equal to 2 times 2x is 4x, 2 times negative 3 is negative 6. And simplify that, add a negative x to both sides and a positive 6 to both sides. So we'd have 7 equals 3x. X equals 7 over 3. Just a little simple fraction there for an answer. Last part in Lesson 5, logarithmic equations. Apply your logarithm laws from Lesson 2 and 3 to solve for the unknown. And the example and practice set solutions, they'll be integers or simple fractions, so nothing too big or fancy or anything. So just focus on applying your logarithm laws. And so in A, how could we simplify that? Well, we can get that on the left in terms of one value, right? Use our quotient rule and log base 2 of 2x minus 4 over x minus 2 is equal to 5. And then apply just fundamental logarithm rules, log base b n equals L, and we'd have 2x minus 4 over x minus 2 is equal to 2 to the 5th, which equals 32. And so now just simplify that, solve for x. Multiply both sides by x minus 2. So we'd have 2x minus 4 is equal to 32 times x minus 2. Expand that. Let's move over here. 2x minus 4 is equal to 32x minus 64. Rearrange. Minus 30x is equal to minus 60. Divide both sides by negative 30x equals 2. So A, x equals 2. We could substitute back in just to make sure all of that works. So we'd have log base 2 of 2 times 2 is 4 minus 4. Log base 2 of 0 minus log base 2 of 2 minus 2 is again 0. Log 0 minus log 0. That does not equal 5. Log 0 is undefined, so we would just say no solution, or we could write the empty set symbol. Either one there. So we don't say x equals 2. We say that there's no solution. In B, this one's going to take a little bit more thought, but just remember that log, when we just see log like that, that means log base 10. And start by changing the square roots, the radical signs, to fractional exponents. So let's do that. Let's just write log of x to the 1/2 power is equal to parentheses log x to the 1/2 power. So those are different things. On the left, we can apply the power rule and say half log x, that's equal to log x to the 1/2 power. How do we get rid of that 1/2 power on the right? Well, we could square both sides, right? Square that. Square that. 2 times 1/2 is 1. On the left, we'd end up with half times half is 1/4 log x, that quantity squared, is equal to log x on the right. Set that equal to 0. 1/4 log x squared minus log x equals 0. We could factor a log x out of that. Log x times 1/4 log x minus 1 is equal to 0. Now find the zeros. Log x equals 0. That's one of them. When does log x equal 0? Well, when x equals 1, right? Logarithm of 1 equals 0. 1/4 log x minus 1 equals 0. So on that one, we'd say log x equals 4. When does the exponent equal 4 for a base 10 logarithm? Well, when x is 10,000, right? When x is 10,000. So there's our two solutions. X equals 1, x equals 10,000. So does that work? And really what we're looking for there is if we substitute those back into the original equation up here, are we going to get like a logarithm of a negative number or a logarithm of 0? Well, no, we're not. Square root 1 is log 1. That's 0. Square root log 1 is square root of 0. That's 0. So that works. 10,000 works as well. You can check it if you want to, but it does work. X equals 1 and 10,000. Those are the two solutions for B. Or you might even say x is 1 and 10 to the 4th, or x is 10 to the 0 and 10 to the 4th. You can say that as well. And that is all for Lesson 5.